Okay, so we'll be solving exercise 2.1 question number 12. Prove for every integer k greater than or equal to 1 that the following expression, which we write as a function of k, is an integer. We'll prove this by induction. So base case, we take k equal to 1. When we plug in k equal to 1, basically f of 1 turns out to be 1, which is an integer. So for k equal to 1, the expression is an integer. So we have proved the base case. Now we move on to the inductive step. In the inductive step, we'll assume that f of k is an integer for some k, and what we need to prove is that f of k plus 1 is also an integer. So we're going to use f of k is an integer to prove that f of k plus 1 is also an integer. Now how do we do that? We write f of k plus 1 as f of k plus f of k plus 1 minus f of k. We already know that f of k is an integer by the induction hypothesis. All we need to do is prove that f of k plus 1 minus f of k is also an integer. You'll see that this has an easy form and we can easily prove that this is an integer. So we compute f of k plus 1 minus f of k. All I've done is plug in k plus 1 and k into the original formula of f of k to get the expression. Now there are three terms, so we'll simplify each of the three terms separately. We are expanding k plus 1 power 7 by the binomial theorem and then subtracting k power 7 and then dividing by 7 to get the resulting equation. Similarly, we expand by binomial theorem for k plus 1 power 5 and do the necessary calculations to get the following expression, and similarly for the third term. Now there are two parts in each of these three equations. One is the polynomial part, that is all the terms containing k, and the fractional part, that is all the numerical parts that are fractions. So we add all of the fractional parts, and when we add the fractional parts it results to 1. So we can write f of k plus 1 minus f of k. So when we compute the polynomial parts, of the three equations, when you add up all the polynomial parts, you get the following expression. Now we can write f of k plus 1 minus f of k as the polynomial part of the expression, which I showed before, plus the fractional part, which is 1. Now in the polynomial part, each term is k power something and an integer coefficient. Now since k is an integer and the coefficients are also integers, f of k plus 1 minus f of k is also an integer. So we have f of k is an integer by the induction hypothesis, and f of k plus 1 minus f of k is an integer as we proved. So f of k plus 1, which is equal to f of k plus f of k plus 1 minus f of k, that is also an integer, and hence by induction we have proved that f of k is an integer for all k greater than or equal to 1.